Thank you very much. Our next paper is 5 Energy Generations of Tall Buildings, a historical analysis of energy consumption in high-rise buildings. And here to present the paper are Philip Oldfield and Dario Trabucco. Philip Oldfield is with the Institute of Architecture at the University of Nottingham, where he is pursuing a PhD in tall buildings entitled Toward Carbon Neutral and sponsored there by OV Arab Limited. Philip is also a member of the Tall Buildings Teaching and Research Group and has done a number of teaching and research in that area. Dario Trabucco, who is present but as I gather will not be presenting, is with the Faculty of Architecture at the Università di Venezia, and he is also engaged in a PhD on building technology focused on tall buildings and specifically on the design of service cores.
Thank you very much. Good afternoon. This presentation, the 5 Energy Generations of Tall Buildings, examines a categorisation of tall buildings based on their energy consumption characteristics. What I mean by that is that we've chronologically grouped together tall buildings by factors that affect their energy use. So shape and form, lighting strategy, façade performance and opacity, ventilation strategies. So a quick look at our presentation agenda. Firstly, I'm going to look at some existing categorisations of tall building. I'm going to quickly then jump on to our categorisation of tall buildings, which are based on these 5 energy generations. Whilst talking through that, I will look at some influences, some outside influences that have affected energy use in tall buildings, such as regulatory changes, technological developments, and changes in architectural thinking. I'll also touch on the future as well. So there've been, across time, there've been numerous categorisations of tall building. This one's quite well known based on architectural style. You can group together tall buildings based on their structural strategy, for example. I'm sure everyone's seen this diagram. Or alternatively, you can group together tall buildings based on their function. Now, what myself and Dario noticed is that very little work has been done to potentially group together tall buildings or classify them based on their energy, or more specifically on factors that affect their energy. And this was very much the starting point for our research. So with this in mind, we have defined 5 energy generations, which I will now run through. Now, the first energy generation is from the birth of tall buildings in the late 19th century to the 1916 New York zoning law. And it refers to the early skyscrapers of Chicago and New York. And the first thing to note about these early buildings is their form and shape. Buildings covered the majority of their lots. They were vertical extrapolations of a similar plan, and they rose up to considerable heights. And this was driven by a desire to maximise the floor area. And this can be seen, this is a view of New York in 1911. So these buildings had a compact and bulky shape with a large volume per unit surface area. The next characteristic of note is a façade. There are high levels of thermal mass within these early buildings, within the façades. While the latest developments in steel frames freed the envelope from any structural role, it still maintained an influence by traditional load-bearing structures. So external walls were thick, masonry construction, and often had a plasterwork internal finish. So that gave the façade a high quantity of thermal mass. Also, there is a low percentage of façade transparency. If you compare a façade from the early 20th century to a modern façade, you can see there's a significantly reduced quantity of transparency. Ventilation in these early buildings was naturally achieved via openable windows, and artificial lighting levels were typically very low due to inefficiencies of the technology of the time, usually around 2 to 4 foot candles in office buildings in 1913. So because of all this, we can say of this first energy generation that the main consumers of energy were heating and the elevators. A really good precedent for this generation is the Equitable Building, constructed in New York in 1915. It's got a massive bold shape which displays a large volume versus small surface area. Its facade is only 25% built up of glazing. In fact, the building was so massive that it cast a 7-acre shadow across New York, and it blocked out the sun and sky on similar surrounding buildings. And this was a catalyst for the 1916 zoning law, which defines the second energy generation. Now, the second energy generation was these buildings that followed the 1916 New York zoning law, and it's characterized by the familiar wedding cake style of skyscraper. The 1916 New York zoning law was put into place to preserve light and air onto the streets below, and it did this by requiring buildings to use setbacks, which, as I say, generates this well-known wedding cake style of skyscraper. Now, in order to determine the influence the zoning law had on tall buildings of its time, we studied 10 tall buildings, 5 from before the zoning law and 5 from after. For each building, we calculated its surface area to volume ratio, and that involved calculating the surface area of the Chrysler building and all sorts of complicated calculations. But basically, what we found was, to be quite expected, that the tall buildings after the zoning law had an increased amount of surface area per unit volume. In fact, they were more slender. Now, what does this tell you in terms of energy use? Well, studies show that in places with colder winters, such as New York, the surface area to volume ratio is directly proportional to the winter heating loads. So we can quite clearly say that after the New York zoning law, the tall buildings had higher winter heating loads. But however, the slenderness of the tall buildings allowed for more natural light to be penetrated into the shallower floor plans. Now, although this study was in New York, this style was copied in many cities across North America at the time. So the first characteristic of a second energy generation is a slender shape. There's still high quantities of thermal mass in the facade and a low percentage of facade transparency. And it's also within this time period that air conditioning became more commonplace in tall buildings, although it wasn't in every tall building. It was like it was in the post-war era. There was an increased requirement for artificial lighting, and this was driven by aggressive sales tactics of large power companies within the 1930s. So moving on now to the third energy generation that we've defined, and this generation deals with the paradigm shift from the kind of traditional solid thermal mass facade to the glazed curtain wall facade. And arguably this technological development, along with fluorescent lighting and air conditioning, was important to the transformation of post-World War II skyscrapers as the elevator and steel frame were at the end of the 19th century. Fully glazed designs were around from the early 1920s. I mean, these were by Mies van der Rohe, but obviously way ahead of the technological developments of the time. However, by the 1950s, the technology became available, and one of the first to utilize this was the Lever House in New York. Now, its facade was a single glazed, tinted curtain wall with a concrete upstand. The upstand was for fire legislation purposes. So what's the impact of this paradigm shift to a more transparent facade? Well, if you look at the facade performance of second energy generation buildings, for example, the Empire State Building, only 23% of the facade was single glazed, and it had an average U value of about 2.6. However, by doubling and further the percentage of single glazing within the facade, you create a significantly inferior facade performance. And you can compare that against modern facades which have, double, triple glazing, E-coatings and argon fillings. And buildings with higher quantities of single glazing also were found in this area. I mean, this is Lakeshore Drive Apartments, and it didn't need the concrete upstand. So it had 72% of the facade was single glazing. It had an average U value of around 4.2. So the first characteristic we can say of third energy generation buildings is they had a low performance single glazed facade. Again, high levels of transparency within the facade. But despite this, there was a continued reliance on fluorescent lighting. This table shows Illuminance recommendations in the USA from 1915 to 1982. And it's within this time period, in the third energy generation, that these figures are at the highest, around 200 foot candles for office spaces. The facade design of tall buildings of this era consisted of fixed glazing as air conditioning had become more commonplace. The single glazing resulting, everyone knows single glazed tall buildings, you're going to get high heat losses in the winter and excess solar gain in the summer. And these were the first generation of tall buildings where air conditioning was so fundamental to the design that they couldn't function without it. In terms of shape, tall buildings of this era were, again, returned to a compact and bulky form. And this is highlighted again by looking at this graph. Again, we took another 5 buildings from this era and calculated their surface area to volume ratio. And they showed an increased level of compactness and bulkiness. Now, this happened for 2 reasons. Firstly, the 1916 zoning law was replaced by the 1961 zoning law, which allowed for a more bulkier building as long as you planned a plaza with a building, which is why you see buildings like the Seagram building with a large plaza in front. The second reason was that deep office floor plans, companies had struggled in the shallow office floor plans of the 1930s tall buildings, so the economy had driven tall buildings towards the creation of a deep office floor plan. Now, another very interesting characteristic of tall buildings of this time, the third energy generation, is a large quantity of black skyscrapers constructed in this era. Influenced by Mies van der Rohe's early designs, these appeared in all across North America, as well as Paris and Tokyo, all within this era. Now, what is the building energy consumption impact of a black skyscraper? Well, the first thing to note is that black and darker colours have a higher solar absorbance than lighter materials, and this may result in things like excess heat gains in the summer and the urban heat island effect. And that's shown in the top table. The second characteristic to note is that many of these black skyscrapers used a bronze or grey or dark coloured glazing to complement the black cladding. The Seagram building, for example, used a bronze glazing. Now, the impact of this is that despite the high quantities of glass within the facade, not very much natural light would penetrate through the glazing because of its colour, because it's low light transmission levels. And this goes away to show how these buildings were so reliant on fluorescent lighting despite being 50-75% glass. Now, to sum up the third energy generation, it's worth looking at this graph, which shows a survey of building energy consumption for 86 office buildings in Manhattan. Now, you can see that tall building energy consumption grew dramatically within this era of the early 1950s to 1970. This study shows that completed buildings in the late 1960s used almost twice as much energy as those completed in the early 1950s. The next energy generation was triggered by 2 events in the 1970s, the Energy Crises of 1973 and 1979. Now, the 1973 energy crisis made building energy consumption a major issue for the first time, and also more research into glazing systems, gas-filled cavities, e-coatings, for example. So the major difference between the third energy generation and the fourth energy generation was in terms of facade performance. The facade transparency remained high, and thermal performance was dramatically increased by this new research that had gone into the glazing systems. Lighting recommendations to offices were reduced following the energy crisis as energy in buildings became a more important factor. But tall buildings still were hermetically sealed buildings and almost totally reliant on mechanical conditioning, and still demonstrated a compact shape. However, whereas the third energy generation saw a vast number of black skyscrapers constructed, the fourth generation saw this figure dramatically increase. Myself and Darry did a study where we looked at tall buildings over 100 metres in North America, or black tall buildings over 100 metres in North America. At the peak in 1971, 17 tall buildings were completed. However, following the years of the energy crises, when energy levels in tall buildings became more important, there was a substantial reduction in the number of black skyscrapers, down to 0 in around 1977. One of the major tall building casualties of this move away from the black skyscraper was the Tour Elf in Paris. Now, it was originally designed to be a twin black skyscraper to the Tour Fiat, as shown on the right-hand side. However, the 1973 Energy Crisis put the developers off doing this, and they redesigned the Tour building using a high-performance facade and a building management system. And the result is the building is of the same height and gross floor area as the black skyscraper, but is half as expensive to heat and light and maintain. The last energy generation is the fifth energy generation. Whilst the majority of tall buildings today, I would say over 95%, continue to be constructed with fourth energy generation characteristics, there is a small but growing number of completed buildings and proposals that make reducing their energy consumption the driving point for their design. While one could argue that these tall buildings have been around for many years, almost back as far as the Price Tower in Oklahoma in the 1950s, for myself, arguably the first major tall building that showed of its generation was the Commerzbank in Frankfurt. And it used ideas such as a central atrium for light and ventilation, sky gardens to allow more natural light into the building. Also used a facade that allows some natural ventilation over half the time of the year called the Klima facade. So for the first time in around 50 years, tall buildings were again being designed with openable windows. Tall buildings of this generation tend to have a more slender shape, and this is brought on by the importance of natural light. So they tend to be either a more slender building, or they use atria and natural light to create a larger facade area to allow for closer people to sit close to natural light to reduce artificial lighting levels. They generally have a very high performance dual skin and triple glazed curtain wall facade systems. There's still high quantities of facade transparency within these buildings. And natural light penetration is maximised, often with the utilisation of photo and motion sensors. And one of the other major points within tall buildings of this generation is opportunities for natural or mixed mode ventilation are exploited where possible. This is a GSW headquarters in Berlin, which uses a double skin facade using the stack effect. It essentially uses it as a thermal flue to naturally ventilate the building for about 50% of the year. This is a dual skin facade in the Deutsche Post Tower in Bonn. And the last kind of trait of fifth energy tall buildings, and this is a quite recent one, is on-site energy generation is promoted. Buildings such as 4 Times Square, which uses fuel cells. There's the CIS Tower in Manchester, where the core has been reclad in solar cells, and probably the most exciting tall building development in a few years, which is the Bahrain World Trade Center, where wind turbines will generate a significant proportion of the building's energy. And future proposals are even more exciting. So just to summarise, these are the 5 energy generations that we've defined. There's the first energy generation from the birth of tall buildings to the 1916 zoning law. The 1916 zoning law changed the shape of tall buildings, made them more slender. Then the third energy generation, that was a paradigm shift from a solid thermal mass facade to a glazed curtain wall. The fourth energy generation, influenced by the energy crisis, improved facade performance, and fifth energy generation buildings are influenced by a reduction in their energy levels. So I just want to quickly mention the future. Now, as I've said, I would say the majority of tall buildings today are constructed to fourth energy generation characteristics, 95% at least. Buildings that perform to building regulations but don't push these any further. With climate change, arguably the greatest challenge of the 21st century, I believe a paradigm shift to the fifth energy generation is necessary if we are to meet these carbon reduction requirements. And another point of note on tall building facade design. Now, ever since the 1950s, the glass curtain wall has been the facade design for tall buildings, even into fifth generation buildings, these buildings where they're heavily influenced by reducing their energy. Is there a possibility to be inspired by these earlier tall buildings, had a larger quantities of thermal mass within the facade? And these are some Ken Shuttleworth make designs, and I'm sure, or Ken's presenting here, I believe tomorrow, so he'll pick up this point a bit more, I believe. I just want to finish with our results table, which is in the Congress proceedings, and this outlines, we've studied over 25 buildings from each different generation, and it summarises the various figures that myself and Dario have come up with. Thank you very much.